Hi everyone, my name is Xiaotong Chen. I'm currently a PhD student in the robotics department at the University of Michigan Ann Arbor. Today I'm going to talk about a project named ProgressLabeller, Visual Data Stream Annotation for Training Object-Centric 3D Perception. The work is completed together with Huijie Zhang, Zeren Yu, Stanley Lewis, and advised by Professor Chad Jenkins. Our project is motivated by such a scenario. Suppose we have a robot and a set of objects. We want to do some vision-based manipulation tasks. And taking advantage of recent progress in deep learning, we have a bunch of models like detection, segmentation, or pose estimation. But actually, the bottleneck is how we can get a customized, large-scale, high-quality real data set. Our proposed solution is to use an open source system to enable fast dataset creation. So this is a snapshot of the user interface of ProgressLabeller. So we implement that as a UI in Blender. So on the left part is currently a 4-view RGB image. So they're from different views, and we overlay the object 3D model in wireframes, where we can see their silhouette match with the backend RGB images from different views. So backend, the underlying assumption is that if the pose is correct, it should be correct in multiple views. The top right and top down are operation panels. This is the first step to use the ProgressLabeller. So we need to get a camera trajectory estimate. And currently we use the backend of Object-Centric that can work on some hard objects like reflective or transparent objects. So if it came to hard, like dark environments, we can switch to depth-based fusion system. Suppose we have estimated camera trajectory. We know the correspondence of every RGB image. Then we can annotate by dragging the object in 3D space. So in this case, we finish aligning a plate with the RGB image, and then we come to a bottle-shaped object. So basically, the step is to iteratively turning the shape, the position of the object until it matches with the RGB silhouette from different views. And every time of marking one object is like 20 or 30 seconds. Yeah, now the bottle-shaped object is aligned. We find the third object, a water cup. Still, we choose one of the RGB views and to align that. Then we use the other views to do cross-checking. Then we can upload the object for every individual frames for the entire video sequence. So here we overlay the segmentation mask and 6D pose to the RGB images. And this can be used for training current deep networks. We did several experiments to verify the results. First, we compare the annotation accuracy with the previous baseline called Label Fusion, which uses elastic fusion to fuse steps and solve camera pose. We collect several public datasets like HOPE and YCP video. They are with feature-rich objects, and OCS is on category-level objects. TLS is object with texture lists. And then this is some quantitative results, and we can see that the ground truth annotation for HOPE is not that good, as we crop the images by rendering the object at their labeled pose. And compare with Label Fusion, our ProgressLabeller is more aligned with the object RGB image. And we also have some quantitative results. So here we evaluate mask IOU with ground truth, pose error in position and rotation. And ADD and ADDS are average 3D point distance. This feature pixel is that we render the object given their labeled pose and extract shift feature, and also compare that with extracted shift feature from the raw RGB image and calculate the distance. So the lower means the ground truth is better. So here we can see ProgressLabeller is better on HOPE and OCS and TLS, while on YCP video dataset, the feature pixel is pretty higher, much higher than both annotated methods. It means the ground truth is not that reliable. Then we did the second experiment about evaluation of pose estimation and grasping. So here we collect several videos of the YCP objects using 3 different cameras for validation. We annotate the object pose using both ProgressLabeller and Label Fusion. And to also compare with data synthesis, we use a Blender prog to kind of render the objects to the labeled pose. So here you can see the difference between the left image synthesized and the right raw RGB. The difference is pretty trivial. We did this similar for the depth image. Then we can train an RGBD pose estimator for each of the datasets. Here we use FFV6D from a CPR 2021 paper. And then we can evaluate their pose estimation and do robot grasping experiments. So on the left is the pre-trained model and the fine-tuned model. We can see after fine-tuning, most of the poles are much more stable. On the right is we use the pre-trained and fine-tuned model for robot grasping. We can find that after fine-tuning, the robot is able to do better grasping and manipulation. Yeah, these are some quantitative results. So we divide the table to different individual objects, and the grasp tolerance is the difference between the maximum gripper distance to the object diameter. Then we compare to 4 categories: pre-trained, blended prog, label fusion, and ProgressLabeller. So the latter 3 are fine-tuned on the label annotated using these methods. You can find ProgressLabeller has the best average ADD error and the grasp success rate. So to conclude, we contribute such a fast, easy-to-use data annotation pipeline that can also work on transparent objects. And we improve the deep estimator accuracy and grasp success rate through fine-tuning. There are 2 main feature directions. One is to estimate the object's 3D shape online, so we don't need to depend on CAD model. The other is to support dynamic scenes. Yeah, that's all. Thank you. Any questions?